Okay, let me start. Okay. Uh, Parametric methods in reliability analysis also can be used um, generally to analyze the reliability in the systems. And these methods are statistical approaches that assume the data follows a specific probability distributions. And commonly used distributions include the exponential, variable, and normal distributions, so each of which is suitable to different types of failure behavior. And in these methods, the collected data can be used to estimate the parameters of the chosen distribution, such as scale and shape parameters and so on. So once these parameters are determined, you can model the failure behavior of the systems and predict important reliability measures such as a lifetime failure rate and survival probability. So, and parametric methods are widely can be used because they provide powerful and um, interpretable models, but they rely on the assumption that the selected distribution accurately represent the underlying data, and this is the some issues that we have for this kind of methods. Okay, parametric models relies on several key assumptions to ensure that the analysis and the results are valid and can be applied for those for the application. First, it is assumed that the data follows a specific probability distribution, such as the variable or exponential distribution. This means that the selected model must accurately represent the underlying behavior of the data. And another important assumption is that failure behavior is consistent and predicted over time, and allowing for reliable modeling, and it will make some problem for us. So this one also should be taken into account in the modeling. Additionally, observations are assumed to be independent, meaning that the failure of one unit does not affect another one. And the parametric methods also assume that the parameters of the model remain constant throughout the analysis. If these assumptions are not met, the results may be inaccurate, so it is important to carefully validate the model before using it for reliability predictions. And we have another we already talked about the exponential distribution. So as you know, the exponential distribution is one of the simplest and most widely used models in reliability engineering. It is particularly suitable for systems that exhibit a constant failure rate over time, meaning that the likelihood of failure does not depend on how long the system has already been in operation. So this is one of the uh, key feature of this method. And this property is known as the memoryless property, which makes the exponential distribution mathematically convenient for modeling random failure processes, and can be applied regularly for this kind of applications. And the probability density function is defined in terms of the failure rate parameter, lambda, which represent the rate at which failures occur. And this distribution is commonly used in reliability analysis of electronic components and other systems where failures occur randomly and independently over time. So, okay. The variable distribution is one of the most versatile and widely used distribution in reliability engineering because it can model different type of failure behavior depending on its parameters. We already discussed about both of these distribution functions, but I just want to refresh your mind because we need in following slides those information. And it is defined by two main parameters, as I told you before, the shape parameter beta and scale parameter eta. And the shape parameter play a crucial role in determining the nature of the failure rate. When beta is less than 1, the failure rate decreases over time, which is typically of early life or infant mortality failure. So um, we can bearing in mind those things in when we want to investigate the variable distribution. When beta equals 1, the distribution behaves like the exponential distribution, including constant failure rate. Let me add another student. So as I told you, when beta equals 1, the distribution behaves like the exponential distribution, indicating a constant failure rate. And when beta is greater than 1, the failure rate increases over time, representing wear out failure. So, and due to its flexibility, the variable distribution can be widely used in analyzing both mechanical and electronic systems and is a key tool in live data analysis. Here, I just added the application of the variable distributions. Okay, another distribution function is normal distribution, also known as the Gaussian distribution, and is one of the most fundamental probability distributions used in reliability and statistical analysis. And it is characterized by its symmetric bell-shaped curve, which is centered around the mean value denoted by mu and spread according to the standard deviation sigma. So we already, I already show you the normal distribution in the figure like this, you know. So we have a mean value and standard deviation sigma. This distribution is particularly useful for modeling naturally occurring variations such as measurement errors, material properties, and manufacturing tolerances. And the normal in normal distribution, we should assume that most values cluster around the mean, with fewer observations appearing as you move further away from it. So, due to its mathematical properties, as you can see in this slide, and prevalence in nature and engineering systems, this distribution function is widely used in reliability analysis and quietly, and it can be used in control applications. So another subject is parameter estimations, maximum likelihood estimation, or MLE. So parameter estimation is a crucial step in parametric reliability analysis and maximum likelihood estimations, or MLE. This estimation is one of the most commonly used methods, and the main idea behind maximum likelihood estimation is to determine the values of the model parameters that make the observed data most likely to occur. On the other hand, it finds the parameter values that best fit the given data set according to the assumed probability distribution. And maximum likelihood estimation can be widely used because it is statistically efficient and can be applied to many different types of distributions, such as exponential and variable. It also provides consistent and unbiased estimates under certain conditions, making it a powerful tool for modeling reliability data and predicting system behavior accurately. So I added several examples at the end of in this slide, but I also will add some examples related to each of these methods later on. Okay, goodness of fit test. Uh, it can be used in reliability analysis to determine how well a selected probability distribution represents the observed data. And this test compare the actual data with the expected values predicted by the model to assess the level of agreement between them. So common methods include the chi-squared test, which compares observed and expected frequencies. And this method is very difficult to pronounce. Kolmogorov Smirnov. It means that they are a Russian name. Tests which evaluate differences between the cumulative distributions, and we have another test, Anderson-Darling test, which gives more weight to the tails of the distributions. And the results of this test help you to make a decision whether a chosen model is appropriate or whether a different distribution should be used. And by validating the model in this way, analysis can ensure more accurate and reliable predictions. Okay, the reliability function is a fundamental concept in reliability engineering that represent the probability that a system will operate without failure behind a separate time. And it can be typically expressed as RAT. Also, we already saw this equation, which denotes the probability that the lifetime of a component or system exceeds time t. And estimating this function is an important part of reliability analysis as it provides insight into how a system performs over time. And this estimation is usually performed using parametric models and statistical methods such as maximum likelihood estimation and so on. By analyzing observed data and fitting an appropriate distribution, you can estimate the reliability function and use it to predict the survival probability of a system, which is essential for design, maintenance, and the decision making process. Uh, I already also um, introduced this one in my previous slides, and I um, explained in more detail about this function. All right. The hazard function analysis, also known as a failure rate function, is a key concept in reliability analysis that describe the instantaneous rate of failure at a given time, assuming the system has survived up to that point. So It is mathematically defined as a ratio of the uh, probability density function over to the reliability function. This function provides important insight into how the risk of failure changes over time. For example, an increasing hazard function indicates wear out failures, while a decreasing hazard function suggests early life failures, and a constant hazard function represents random failures. By analyzing the hazard function, you can better understand failure behavior and make informed decisions regarding the maintenance or design improvements and reliability predictions. We will see all of these in some examples later. So parametric methods offer several important advantages in reliability, advantages and limitations in reliability analysis. So they provide efficient and precise estimates of reliability metrics when the underlying assumptions are satisfied, and they allows you to model complex failure behaviors using well-known statistical distributions. One of their key strength is the ability to extrapolate behind the observed data, which is especially useful for predicting long-term reliability and making informed design decisions. However, these methods also have limitations, and they rely heavily on the assumption that the chosen distribution accurately represent the data, and any misspecification can lead to incorrect results. Additionally, parametric methods may not perform well when the data set is small or poor quality, and they may not adequately capture all types of real-world failures behaviors. Therefore, careful model selection and validations are very essential here. Okay, this is a section 7 about non-parametric methods. So non-parametric methods are statistical techniques can be used in reliability analysis that do not rely on the assumption of a specific probability distribution. So instead of fitting the data to a predefined model, these methods use the observed data directly to estimate reliability measures. So this makes them highly flexible and particularly useful when the underlying distributions of the data is unknown or difficult to determine. So common parametric techniques include the Kaplan-Meier estimator and Nelson-Allen estimator, which are widely used for analyzing survival and failure data. And these methods are specifically valuable when dealing with sensor data or incomplete data sets, as they can still provide reliable estimates without strict assumptions. And I will back again to different type of the data by giving you some more example about those concepts. So we will discuss today or next week about that. Sorry, 1 minute. Okay, the first estimator is a Kaplan-Meier estimator. The Kaplan-Meier estimator is one of the most widely used non-parametric methods for estimating the survival or reliability function from observed data, especially when sensor data is present. It works by calculating the probability of survival at each observed failure time and then multiplying these probabilistic together to obtain an overall survival estimate. So this results in a stepwise survival curve that decreases at each failure event. One of the key strengths of the Kaplan-Meier method is its ability to handle sensor data effectively, which makes it highly practical for real-world reliability analysis where not all units fail during the observation period. And this method provides a clear and initiative way to estimate reliability without assuming any specific underlying distribution. So, as I told you, I will add some examples also regarding this one later in the PowerPoint. So another estimator is Nelson-Allen. The Nelson-Allen estimator is a non-parametric method used to estimate the cumulative hazard function, which represent the total accumulated risk of failures over time. Unlike parametric approaches, it does not assume any specific probability distribution and making it highly flexible for analyzing real world data. And the estimator is calculated by summing the ratio of the number of the observed failures to the number of units at risk at each failure time. And this produces a stepwise estimate of the cumulative hazard, which increases as time progresses and more failures occur. And then the Nelson-Allen estimator is particularly useful when dealing with sensor data and is often used alongside the Kaplan-Meier estimator to provide a more complete understanding of reliability and failure behavior. And it will play an important role in survival analysis and risk assessment in reliability engineering. So there are so many applications for those estimator. Okay. Life table analysis also is a non-parametric method used to estimate and summarize reliability and survival data over time. In this approach, the total observation period is divided into smaller time intervals, and for each interval, key information such as the number of units at risk, the number of failures, and the survival probability also will be recorded. And this structure tabular format allows you to analyze how reliability changes across different periods, and one of the main advantage of live tables is their ability to handle large data set and provide a clear overview of survival trends even when the data is grouped. And this method is I added the application of each of the methods at the end of the explanation. So this method is widely used in both engineering and medical studies to evaluate system performance and understand failure patterns over time. Because there are some biomati- bio, biomedical engineering in the class. That's why I added this method in this slide. Okay, parametric and non-parametric methods differ primarily in how they approach reliability analysis. So parametric methods rely on assuming a specific probability distribution such as the Weibull or exponential distribution and use this model to estimate reliability measures. In contrast, non-parametric methods do not assume any underlying distribution and instead work directly with the observed data. This makes non-parametric approaches more flexible and particularly useful when the true distribution is unknown or difficult to identify. While parametric methods can provide more precise estimates when the model is correct, they can lead to inaccurate results if the our initial assumptions are wrong. So non-parametric methods such as the Kaplan-Meier estimator are simpler to apply and are especially effective when dealing with sensor data. And each approach has its strengths, and choose between them depends on the nature of the data and the analysis objectives. And in this table, you can see the comparison of these two methods together. Okay, non-parametric methods. In this slide, I just want to mention the advantages of non-parametric methods. Non-parametric methods offer several important advantages in reliability analysis, primarily because they do not rely on any assumed probability distribution. And this makes them highly flexible and applicable to a wide range of data sets, especially when the underlying failure behaviors is unknown. These methods are also particularly effective when dealing with sensor data as they can incorporate incomplete observations without requiring strong assumptions. Another advantage is their simplicity and initiative nature, which makes them easier implement to implement and interpret compared to parametric models. Additionally, non-parametric methods are so robust to model misspecification. As a result, they are widely used in real-world reliability studies where data may be limited or there is some uncertainty parameters. Okay, while uh, so here I want to say some disadvantages or limitations of these methods. While non-parametric methods are flexible and useful, they also have several limitations. One of the main drawbacks is that they tend to be less precise when working with small data sets, since they rely heavily on the available data without any distributional assumptions. Additionally, these methods have limited ability to extrapolate beyond the observed data, which means they are less effective for long-term reliability prediction. Compared to parametric methods, non-parametric approaches generally provide lower predictive power because they do not model the underlying distribution explicitly. And they can also be more sensitive to variability in the data, which may affect the stability of the results. Finally, non-parametric methods provide less insight into the underlying failure mechanisms, as they focus more on data-driven estimation rather than modeling the physical behavior of the system. That the key takeaway in section 8, I just want to summarize and conclusion the all of sections. The key takeaways from these lectures highlight the importance of reliability testing and data analysis in engineering systems. And reliability testings, as I mentioned before, plays a crucial role in ensuring that products and systems perform as expected while minimizing failures and risk. We already discussed about accelerated live testing, helps reduce both time and cost by simulating long-term usage under accelerated conditions. And proper test planning and sampling are essential to obtain high quality and meaningful data. And in the real world applications, sensor data is very common and it must be handled carefully using appropriate methods. So both parametric and non-parametric approaches are important tools in reliability analysis, and the choose the choose between them depends on the nature of the data and the assumption that can be made for that applications. Ultimately, selection the right model and method is critical for achieving accurate and reliable results. So this is a main point. All right. Um, Reliability testings. Also, we discussed about applications. Just I want to summarize again. Reliability testing and data analysis have wide-ranging applications across many industries where system performance and safety are very critical. In the aerospace industry, reliability analysis is essential for ensuring the safety of complex systems such as aircraft and spacecraft. In the automotive sector, it is used to evaluate the durability and long-term performance of components and systems. The electronics industry relies heavily on reliability testing to analyze failure mechanisms in circuits and devices. In energy systems, particularly renewable energy integration, reliability analysis helps optimize systems performance and reduce downtime and so on. Additionally, in the medical field, reliability is critical for ensuring that device function correctly and safely, directly impacting patient health and safety. And these applications demonstrate the importance of reliability engineering in real world systems across multiple domains. Okay, in this slide, after this slide, I just want to show you some example regarding this lecture. So I will add more example for the next week also. In this slide, we not only define the key reliability metrics, but we also visualize failure behavior using a simple bar chart you can see in right hand side. So uh, the question is that what is the reliability testing of LED lamps? So a company tests 100 LED lamps to evaluate their reliability. Each lamp is operated continuously until it fails. What reliability metrics can be obtained from this test? So the chart shows the number of LED lamp failures at different times interval: 100, 200, 300, 400, and 500 hours. As we can see, the number of failures increase over time, which is expected because more units reach the end of their lifetime as testing continues. And to obtain this data, we can start by testing 100 LED lamps under continuous operation. So each time a lamp fails, we record its time to failure. So then we group the failure times into time intervals. For example, how many lamps failed before 100 hours, between 100 and 200, and so on. So this group data is used to construct the bar chart, as you can see here in this slide, which provides a clear visual understanding of how failures are distributed over time. This type of visualizations helps you quickly identify patterns such as whether failures are occurring randomly or increasing due to aging effects, and it also serves as a foundation for more advanced analysis such as fitting probability distribution like Weibull and or exponential models. So let me close the session here and have some break